Okay, well, thank you to the organizer to give me the opportunity to give a talk. And thank you for those who could wake up for this morning talk. So this is a work in collaboration, and I'm glad because they are here with Yannick and Noémie, who are there to rescue me. And part of this work has been already given by Noémie at various occasions, short talks, but then we finished the paper. And in fact, I should have written the archive number of the paper, maybe at some point. Anyway, you can find it. So the motivation is to have a global understanding, and global in geometrical global understanding of super BMS. So that's the motivation. One motivation behind our work. Of course, the main motivation is the idea of Penrose of conformal compactification of space-time, precisely in the non-super case, in the usual case, that enables to understand global properties of BMS and to geometrize it to the understanding of asymptotically flat space-time. So here we are interested in, therefore, understanding asymptotic super Minkowski. Space-time. The super will not always be at the same place. Sometimes Minkowski superspace or super Minkowski space-time, that doesn't matter really much. So there are some, of course, there have been some works, preliminary works done on super BMS, but they don't always agree, actually, what it is. And so we before starting with radiation, I wonder whether it will be better like that. Well, yeah, okay. We want to study the empty case, so empty spacetime. So I insist that it's super Minkowski, so empty spacetime. Yeah. So I will have to go away from this place. Exactly in this corner that I should not be. Okay. There is a very specific place, but anyway, I can fill all the blackboards at random, and then that will be a hard job for Eva to help me. So empty super spacetime. First, before looking at supergravity. In fact, we are interested in extended gravity. Yeah.
You're talking about 4 dimensions?
Yes, it will be exactly. It will be 4-dimensional. So in fact, in the first part of the talk, I will review the result on the compactification, conformal compactification of complex, well, 4 bosonic, but extended supersymmetric Minkowski. So conformal compactification of complex, most of the time. So Penrose introduced this twister because it's indeed very useful to study the global properties of asymptotically flat spacetime. So the ideas of BMS and Guérac and all the coworkers could be understood in a nice way via the twister. And here we use super twister to understand the global properties of super Minkowski spacetime. Of course, we invented nothing. Most of these concepts can be found in the book by Manin of complex super Minkowski. So we definitely refer to Manin's book as the main reference for the geometrical definition, proper definition of, well, at least to us, of conformal compactification of complex super Minkowski spacetime. So I will review this. Another motivation behind our work is the understanding of the Newman H space. So I will go not in this very corner. Another motivation is the study of and generalization to the supersymmetric case of Newman cut and heaven H space. So in this same paper that I'm now reviewing, that I will present in collaboration with Yannick and Noémie, we have not only understood the decomposition in various orbits of disjoint offbits of the conformal compactification of Minkowski spacetime, but we also studied the various cuts from points. Typically, we look at points in the usual bosonic case of Minkowski spacetime, and you look from point inside the interior of Minkowski spacetime. You look at the light cones. You send all the light rays at infinity, and you look where they get cut, so asymptotic null infinity. And so in this work, we have done the slight generalization to the supersymmetric case, but that showed some subtleties that we could not imagine before doing it. Okay, so I think these are the main motivations behind this work. So this space is indeed well known. So it's a homogeneous space. So in the complex case, but I will go, okay, if you wish, I will go now to the real case, so that in this real case, this space will be given by the superconformal unextended group, and then there is a stabilizer. We'll just give it Earth. Here it is. So this space is well known, and I will discuss about that. So then, in order to discuss the interior and the asymptotic infinity of super Minkowski, we need to break superconformal invariance. To get super Poincaré symmetry. And the way that we do that is, the usual thing is to introduce a point at infinity through the infinity, in our case, super twister. In this way, then we can discuss of what are points at infinity, what are points inside, and maybe other points that we discover. So in doing that, we therefore decompose the conformal compactification of super Minkowski into various orbits of super Poincaré symmetry. And the result is the following. So again, I write it in the real case, but as usual in twistor theory, it's more natural to complexify and then to study various reality conditions. So one orbit under the super Poincaré group that we find is, not surprisingly, the interior of super Minkowski spacetime. And this is itself, of of course, a homogeneous group. So the super Poincaré group acts transitively on this part, on this orbit. And then there is a stabilizer of any given point, which is Lorentz. And here we have the R symmetry that is there in the orbit. And coordinates on that point, on that space, can be given. Here as well, there is some effect. So a given point, let's say x naught, theta naught, will be given like this. So what else? Then we have what we were mostly interested in, which is the supersymmetric generalization of Schrei, of null infinity, which is again an homogeneous space. So the super Poincaré group acts transitively on this group, on this space, sorry, on this orbit, and the stabilizer as follows. Like this, and I will give coordinates in the following of the talk soon. So these are the orbits that we were expecting to find, but then we found other, in fact, invariant space, I should say, invariant under the super Poincaré group. There is one that we call H, maybe it's unfortunate because it's not related really to Newman H space, but then we have this another orbit I, which is purely fermionic. And finally, we have the points at infinity, space-like or time-like, which are identified in this superconformal compactification. So that's the orbit decomposition that we obtained. So maybe I should write this space, what they are. Well, not exactly now, but a bit more details. So the dimension, as I indicated, the dimension there are 3 bosonic directions and 2n real fermionic directions, whereas the point, the space H here, is given like this. And this is purely, as I said, purely fermionic space, so it's a bit strange. So there is no direction in bosonic direction, only fermionic directions. And this is just a point. Okay, but I will come back to this space. The point is that these two invariant space under the Poincaré, in fact, are not, as we discovered, they are not supermanifold. We cannot give chart on them. We cannot apply the definition of the width on this space, so they cannot qualify as supermanifolds. But nevertheless, they are invariant spaces under super Poincaré. But which means that computation, so we can give coordinates, we can parameterize those spaces, but coordinates should be put between brackets because they don't really define charts, so we cannot talk of these invariant spaces, subspaces, as supermanifolds. They are not supermanifolds in the strict sense. Okay. Okay. Otherwise, like this, so that it can be erased more easily for the German. Is it okay like that? Thanks. Okay. But otherwise, of course, I follow. You are the expert on that. Well, let's continue here. Okay. Yes? Sorry, what? I will describe them. In fact, I will spend time to do that. That's the main part of my talk. Then the second part of the talk concerns the cuts, which I will also discuss I hope, at the right moment. But a picture that could be found with the cut is that, for example, here sky can be viewed as obtained from I, from the supernull cone emanating from this point I. So if you take well, here in the super case, in the supernull cone, which I will define in terms of, well, Manin defines in terms of super ambitwister, you look at this point I, which in fact identified with this one in the compactification, and you look at the supernull cone emanating from this, and you recuperate the whole supersky space. Similarly, we look at various origin for these invariant spaces H and I, and what the picture I can do, let me draw it in this way, in fact, I, is that, as I said, so sky can be obtained by the supernull cone emanating from I. Then there is a space, this space, weird space noted I, which is purely fermionic. So these are fermionic direction. So this dashed line is meant to represent this invariant space under the super Poincaré. And then you take the collection of all the supernull cones emanating from points in this weird, purely fermionic space, and the collection of all these supernull cones is H. We have this understanding through the study of cuts that this page, so you see it has bosonic directions, and it can be obtained as the collection of all the supernull cones emanating from the points in this purely fermionic space. So the dashed line here is the d theta direction. Okay, but now let me review, because I need to, now in some sense the talk can be finished, but I want obviously to give some details, some explanation. For that I need to give my notation so that I can explain a bit more scientifically what we did. So let me then now do a review. I should not spend too much time on the superconformal compactification, and we usually start in the complex case. Let me start by a review of this space with the notion of supertwister. Thanks. Yes, thanks. So for the notation, we have a supertwister given in terms of usual spinors. So we adopted this notation. So these are quantities that are inside C4n, so they are complex entries. But the first four complex entries, A1, A prime. So the first four entries there, they are bosonic quantities, so they commute. And the last n entries they are anti-commuting numbers, complex numbers. So the superconformal group acts linearly on this space, so that's why it is interesting. It's because the superconformal group, in the complex case, the superconformal group acts linearly on this twister. In fact, you see E3. So this bracket is used to say that we have equivalence classes. We can always multiply these 4 plus n complex numbers by a complex number, non-vanishing complex number. So it's really CP3, but we work in that space. So we would simply have a metric, so a matrix in this space, and on Z, it acts as you imagine it does. Okay. So these matrices, X, just to give a bit of information, but they are given by this. So there is the blocks on the diagonal. Divide them as A, B, C, D. So these matrices are super matrices, but they are even super matrices, which means that the blocks A and D on the diagonal, they are made of commuting numbers in the entries, whereas the blocks B and C, they are made out of anti-commuting numbers for the entries. Here we have A, so we denote CA for anti-commuting C numbers, numbers. So here you have 2n rows, and here similarly you have anti-commuting numbers. They are like that, where the Berezinian of X is 1, but it's not necessary. If you win, I can recall, but it's not necessary for the talk that I should recall you what is the definition of the Berezinian. Okay, so the superconformal group acts as the endomorphism group of on this space of supertwistors. Then we like to introduce reality conditions. For that, we need to introduce a Hermitian form. So to impose reality conditions on supertwistor space, introduce Hermitian form, and I will give it in components here. So you take the complex conjugate of a supertwistor, and then there is this invariant, there is this form that can contract, let's say, two supertwistors. And let's say that you can write it in this way. And this matrix here is that. Here we put minus the identity. So for example, if you take one twistor and you take its norm squared in this sense, then you would have by just to be concrete. Okay, and then naturally we can ask what are the set of superconformal matrices that preserve this real form. So to have the real superconformal group, so there you already see that there is this signature with, so if you diagonalize this block there, you see that there are two pluses, two minuses, and then that's the n direction, the harmonic direction. So you ask to preserve from the matrices X in the complex superconformal group that preserves this X. Such that this condition is satisfied. Okay. Now let me discuss about superconformal compactification. And I will distinguish, we like to distinguish the complex and the real cases. So here, let me discuss superconformal. So, and I start with the complex case, which is always easier in this business of twistor. So this complex space, superspace, in fact, as Manin explains, is a flag manifold inside. So you look inside C4n, the two planes inside a set of 2 plus n planes with this signature. So you add the flag for you, the set of these planes, and it can be represented by, it's a 2 plane, so you take 2 super twistor, so B takes 2 values, and in fact, it can be shown that the dual, this space of 2 plus n planes inside C4n actually is the same as the space of such dual super twistors. And then such that, so the fact that they should be embedded, these 2 planes should be inside these 2 plus n planes, translate into the flag condition. That's the flag condition. Okay, so that's the definition, in fact, of the more geometrical we could find of superconformal, compactified, complexified Minkowski space. And this space admits, so this, no, things are not obvious. Actually, you start by describing these planes this way, with a, let's say, big index boldface C, where this boldface C takes, in fact, 2 directions, C for the 1-2 bosonic, and then let's use this symbol C that goes from 1 to n, and it can be shown that it's equivalently described by such a dual super twistor, but I don't think it's obvious. Maybe Yannick, Noémie, you can comment. For me, things are never really obvious. In some heuristic way, the way I like to think is that you have a kind of super volume form with n plus 4 indices. And somehow you dualize these with this epsilon symbol to get this, and then this condition becomes more obvious. Then, so we have this. And there are 2 projections. One, it's by 2. One is on, and that introduces the notion of chiral compactified complex Minkowski space, chiral left, which is the space of 2 planes, so the Grassmannian, with this dimension 2, 0, so inside super twistor space, whereas the other, they give you the compactified complex chiral right space, which is this Grassmannian. Those complex compactified super Minkowski space admits really two projections, left and right chiral complex compactified super Minkowski spaces. And the So the dimension, okay, so the complex dimensions of the spaces, so they have the same. It's for so, okay, if you wish, you have this theta. So Laura, in the real case, so in the 4n coordinates you have at the beginning, 4n complex, they are given there, and I should put some there are direction and there are twistors. So let me put, naturally the indices will come that way, but okay. So 2 plus 2, 4n for I. These are the 4n direction. In the non-chiral case, these are the coordinates that are used to describe this space. But then you have the two projections, whether you use these component directions for the, like this, for the right, and these 2n for the left chiral. And of course, once you impose reality condition, all these four spaces become the same once reality conditions are imposed. And the tilde, theta, becomes the complex conjugate of those ones. But in the complex case, they are viewed as independent, as the usual stuff that we in complexification. Okay, so I think I discussed about that. And so the complex superconformal group acts as you think it acts on these elements. For n, so in the right chiral height super Minkowski space, so you have these dual super twistor B, and you send them x minus 1. So that's the action of SL force n on the dual on the space, on that space here. And I already gave the action on the I can redo it. On the chiral left compactified complex space, this is the action of SL4n, and on the right space, this is the action. So they are still linear, it's still compactified. Okay, so there are three homogeneous spaces under the action of the superconformal group, and in order to find the stabilizer, to see what they are, you look at a given point in it, and you look what stabilizes it. You take any point, and so here so to find the stabilizer, okay, I should put it up. Okay, so what is the stabilizer? Is three superspaces. Well, then let's say for the chiral left space, say in this space, you introduce, let's say, the origin B super twistor. And you take it this way. You take 0. So it's, as I said, so B takes two values. So you have to think of two columns, each column being a super twistor. So in the first two rows, you have zeros everywhere. Then we take the identity 2 times 2 matrix for the third and fourth line of this 4 plus n times 2 rectangular matrix, and then 0 elsewhere. So you take this space, which indeed belongs to the Tasmanians, and you act linearly, as I showed with the superconformal group, and you ask what is the subgroup of the supergroup that preserves that, and you find what you have to find, and that defines for you then this homogeneous space. I will, of course, not give all the details here on the blackboards, but anyway, it's a review. So 4. And the stabilizers is a parabolic, we denote P for a parabolic subgroup of the superconformal group. A similar story obviously applies for the right chiral space. And then for the non-chiral case, you look at the stabilizer of both. So similar. You have not the same, so you don't find the same parabolic subgroup of SL4n, but they are isomorphic. So these two homogeneous spaces, although not identical, they are described by the same homogeneous spaces. And then for the non-chiral case, namely this space where you have both together, so that we, let's say, M left, M right, with the flag condition. You find a different parabolic subgroup, which is smaller, obviously. You need twice as many components as in each of the two chiral left and right spaces. So this subgroup is smaller than the one I denoted here, P0L. In fact, compared to it, you lack 2n fermionic directions, which just expresses the fact that here you have these 4n coordinates, fermionic coordinates in the non-chiral complex space. The dimension indeed is 4 plus 4n. Okay, so now we impose reality conditions. So to discuss the real cases of these various spaces, well, then we take the intersection of both groups in numerator denominator with the subgroups that preserve the Hermitian matrix that I introduced. And I will not go in many more details, but then intersects with the subgroups. This one and that one. Okay, well, of course I can give you exactly the form of these those matrices. Well, if you look at, so you find, when you do the computation, you find a set of matrices inside SL4n, and they have some zeros somewhere because you have constraint, because you need to stabilize this origin B supertwistor. And whereas when you do the same computation where you ask to stabilize both the origin B supertwistor and the dual origin B supertwistor simultaneously, then you have more condition. So which means that the set of matrices is more restricted. So you remove less directions. Right? Yeah. So you remove less, in fact, fermionic directions of this supergroup, SL4n, which means that the quotient is bigger, 4n. Okay, so complex dimension, okay, probably. And the same here. So here, these two n, they really are those coordinates. Here, those two n, theta I a prime, and you have both together in this. Okay. Okay, so then, okay, the real case, I will not go through in detail because now let me discuss invariant subspace. So we now break the superconformal symmetry to look at how the super Poincaré group emerges and what are the various orbits and the super Poincaré group of inside compactified super Minkowski space. Yes? It looks counterintuitive when you know the bosonic case, but it's just like that. It's a fact, and it's explained in the book, that you have a pair of distribution obeying these two properties, these left and right spaces, and that's life. But indeed, when you do superconformal supergravity and superconformal gravity in coordinates, you don't necessarily realize these facts. But then you miss the geometrical origin of these theories of these spaces. Okay, so let me describe the invariant subspaces. And we believe it's necessary to go through that if we want to have a proper understanding of asymptotically flat super Minkowski spaces. Then we introduce, so as I said, we break the conformal symmetry by introducing this infinity twistors. So first we can introduce them. So a pair of direction in super twistor space can be given in terms of an antisymmetric B twistor. And in components, here is this, and 0 elsewhere. In the usual bosonic case, you are always in this block, in this diagonal block, but in the super twistor case, we have also these directions. And then the dual one, infinity super B super twistor, is this. So these, in fact, these B twistors, they are simple. They can be written as antisymmetrized products of two simple super twistors. Like that, two, of course, otherwise it's trivially 0. And similarly, this dual infinity super twistor is also simple. In terms of dual, so left in chiral right, or in chiral right Minkowski space. They are simple. And I can give you the corresponding B super twistors. And 0, 0. This has two rows. Okay, so it's not difficult to see that these two quantities are indeed simple supertwistors. And that allows to pick up some component. There are projectors that will pick up from a supertwistor some of its entries. And in this sense, we break superconformal symmetry. So we can look at the set of matrices inside superconformal that preserve these infinity twistors. So since I showed you how SL4N acts on a twistor in Minkowski left, and this is in chiral right space, we can look at what stabilizes those two quantities respectively, and therefore you introduce the various spaces inside or outside, or at the infinity of Minkowski space. So now because we have introduced these quantities, we can discuss what is inside the interior of Minkowski superspace. So in the Grassmannians, we take the chart where determinant. So we use this quantity, in fact the dual, to select inside of Minkowski left the B twistors, the points that take those components that we denoted pi, and we require this to be non-zero, the determinant. So it's a chart inside of the big space, compactified, complexified super Minkowski space, and that defines for you the interior. So the points inside Minkowski superspace will be given by planes, two planes or Grassmannians with this form. Of this type, where the determinant of this block, this 2 times 2 block, should be different from 0. Now we have the various, we can impose reality condition. We have chiral right as well that we can introduce. So I will try to cut long story short, but show you that the action of, because there are two planes, of course, you can take linear combination of the two supertwistors which are there. So you have this freedom GL to C action. And by using this action, you can, because the determinant of this block is non-zero, you can use it to put the twistor in this way, in this form. Then it's plus A, B, delta A prime. Below B and theta. B. So such a supertwistor, by the action of GL2C, can be put in this form. And this shows that you can identify these GL2C indices there with primed indices. So you recognize the chiral left component, the bosonic component of chiral left Minkowski superspace. And similarly for the interior inside of chiral right Minkowski space, still complex at this stage. So we have finally using GL2C invariance and put it in this way. And Now you can stabilize again a point. So you will take a point particularly simple of this form so that the determinant is non-zero, but you will put 0 most of the other places and call it the origin point in Minkowski superspace. Ask what preserves, what stabilizes this point to discover what are these spaces, interior of Minkowski right and left. They are homogeneous spaces, and what they are will be given. This. So we have the superpoint carré, and where in the terminology for superpoint carré we use is that it possesses the R symmetry group. So maybe it's not standard, but like that. Then maybe it's not illuminating, but I will just once the stabilizer of origin B super twistor. That. Okay. Then again, you can imply a reality condition. Etc. And I will just give you the result that we know very well. Now, imposing reality conditions gives this real superspace. Notice that here it should be really complex. And with the Lorentz, the stabilizer, you recognize the usual Lorentz group, and then the R symmetry. Okay, and then you have the real dimension, which is given there. Okay, maybe I will just make a summary of the coordinates on these various spaces. So we are inside of super Minkowski in the bulk, if you wish. And we have seen chiral left, chiral right complex spaces. We have seen the non-chiral space. And then imposing reality conditions, these three spaces coincide and are given by such these homogeneous spaces. So let's go for the coordinates. Summary. The clock is a bit... It's really like that? No, it cannot be. No, there is a problem with this clock. Okay, then 10 minutes? Okay. 5 even. Really, are you sure? Okay, fine. Boom. So let me see how to cut. Infinity. A cut. A supercut, of course. I will make a supercut. Carrollian superspace. Okay, so now I reviewed what is the interior of the space, but then we can go to another chart. So there was a chart where the determinant there was assumed to be non-zero, but if we assume it to be 0, then we take another subspace of complexified Minkowski superspace, and that will be null infinity. So we'll not make a summary of coordinates. And now take another superscribe, another invariant space. And okay, that's of course still superpoint carré, but well, there is another stabilizer of these points. This reality condition. Then on top of that, as I said, there is other H space, so yet another invariant on the superpoint carré, always invariant. In fact, it will be not a subspace, but invariant space. And which we call this H. Well, they are given by set of the chiral left case. Of course, we look at chiral left, right, and also non-chiral. You can give them in this way. Now we take pairs of supertwister, but where the entries here are not all vanishing in the fermionic directions. So we take a special point in it. We ask to stabilize this point under the action of Super-Poincare. So we find a stabilizer, but in fact, this stabilizer cannot be given true coordinates. Just to give the gist of the information, well, I can do it myself. It's okay. So the trouble comes precisely when you look at the stabilizer of a point there. So you have a set of constraints when you ask to stabilize a special point inside this chart. And typically, you have equations of the form that one of the components in the matrix and Super-Poincare should be of the form, let's say, I or R, let's say for the n extended case, plus a complex m anti-commuting number times one that you took to label this special point. So you take a special point, and there you take one of the coordinates to be non-zero at least, and we call let's call this component A. And so the constraint to stabilize a given point in this chart presents itself in this way. So you might say, okay, very well, so this is given, and I have freedom by coordinates which are we want to call them coordinates which are anti-commuting numbers. But the point is that because it's always multiplied, this m comes multiplied by this anti-commuting number. In fact, it's not a free real coordinate. We cannot define a chart by defining these to vary as we will, because you can always extract a piece which is proportional to A itself times a bosonic commuting number, and that would give zero identically. So viewing this entry as a coordinate of the invariant subgroup of Super-Poincare doesn't qualify to make it a proper supergroup. The stabilizer is not doesn't qualify to be a super Lie group. At the level of Lie algebra, it would mean that the super vector space underlying this doesn't possess a basis. So it's a peculiarity of super vector spaces that not all super vector spaces, although you can give a basis of a super vector space, sub-superspaces may not admit a basis. That's weird, but it's life. Yes, Yannick, you wanted to say. Mm-hmm. Maybe Noémie would be better qualified. You see, we take the approach of the RIT, but which has been proved to be equivalent to more abstract approaches. And you do not work over a field, you work over a ring, the super numbers, lambda infinity, it's a ring. So that makes life quite different. And as I said, there can exist superspaces, sub-superspaces inside super vector spaces which admit no basis. They have no basis. So if you solve the equation, a linear combination of what you would think are vector bases, set it to 0, the solution is not that each of the coefficients is 0. So it's not a subspace. So that's the problem that arises there. It's explained in the book, of course, but here we encounter in this very context of asymptotic super Minkowski space. But okay, still nevertheless, we can describe the points in this invariant. So it's an invariant space on the super Poincare. We can write it in that way, except that it's not super manifold. Okay, so that was for the decomposition, and of course I have to now quickly go to the cuts, the story with the cuts. But maybe since I have really no time to give the details, I can only just repeat what I first said with this drawing, this heuristic drawing. Just redo now, that you look at various points. So now we are in super Minkowski space, so we take a point x, theta, with these coordinates inside of super Minkowski. We send the we take the definition of Manin of super null ways, and we send them, so with direction by A, by tilde A, still working in the complex case. If you vary, so that defines light rays that cut the various invariant spaces, for example, scribe, but also the space H that I briefly described. And you can look where you cut these. You vary these two quantities, H in CP1, and that gives the super null cone. And you look at the intersection of the super null cone in various invariant subspaces of super Minkowski. And so we have done that. We have studied carefully the set of cuts from the interior to the various subspace at infinity, asymptotic spaces for super Minkowski. And we have found in particular that super scry is completely generated starting from this point I by the super null cone emanating from it. I think this is the essence of what I wanted to say. So I think, yes, I have to stop here. Yeah. No, in fact, we didn't think about of that. Well, also, well, this point for us, anyway, they're identified. So I'm not sure that we really have the thing to discuss this. Good question, maybe my collaborators, I don't know, something to say. Here we have identified scry plus and scry minus. When you start from the compactified super Minkowski space, they are identified. Okay, but just indeed to finish, so that was the very initial point before studying what could be a super BMS and globally defined super BMS space. So the space that would preserve this super null infinity. It's the very first step, of course, to continue. But we realized that this was not done, this decomposition of super Minkowski into various orbits under the super Poincare group. We had not seen that elsewhere. And then the space of cuts also is something that could be interesting in terms of character. So setting characteristic data at super scry, we could try to understand the super cut not only in the flat space but in the curved space, and then recover fields inside for supergravity. So characteristic data, so fields from supergravity theory going to, now we better know what is super null infinity. So we can set some data there and go back and solve the super good cut equations. There we solve this equation in the flat space, nothing, no matter, no gravity inside, but obviously now we would like to put supergravity inside the bulk and then solve the deformation of the super good cut equation. Mhm. Yeah, that's yeah. Yeah, it's a good. Yeah, it's a very good question indeed. Now that we have these homogeneous spaces, at least for Sky, not for H, then yes, we can do the nonlinear realization. Yes, and have interpretation in terms of superparticle. I agree. Yeah, that's interesting. So we should look at this paper. Well, I don't think that they describe these spaces in detail, but now we know what is supersquare in terms of a set space, homogeneous space. So your question arises very naturally. I agree. And I should say that what I discussed in this project is also in collaboration with Lionel Mason, obviously, this story I just told just a minute ago about the super good cut equation to solve this work we are doing in collaboration with Lionel Mason. Mm-hmm. Well, so here we look at indeed embedding of super Poincaré inside of super conformal group in both complex and real cases. Yes, in particular, that was part of the computations we had to do. But maybe you have something more intrinsic. Here we work in coordinates, so obviously we have seen some set of matrices, of super matrices inside of super conformal, but it's not maybe what you have in mind. Yeah, there are obviously probably infinitely many ways of embedding super Poincaré inside of super. So here we do with one, but we know they are all the same. So as a homogeneous space, so for example, we picked one point that we called the origin B super twistor, but had we taken another one, obviously we have found the same homogeneous spaces. It's just that the matrices which stabilizes this point would have been different, but still given an isomorphic parabolic subgroup, the same. Yeah. Okay, thank you. Thank you.